Okay, so this is the title of my talk. Thank you very much, Professor Fumiya Sensei. I'm Kenjiro Tadakuma from Tohoku University, and my title, the title of my talk is Beyond Soft Robotic Mechanism. So from deploy, especially this sort of the omnidirectional grippers and the Nemertea proboscis mechanism, and as a result, we are going to build this sort of the robotic blood vessel to self-healing. Self-active healing, right? Okay, so just quickly introduce myself. I really love the mechanism more than 3 times meal in every day. As you can see here, we develop quite lots of the mechanism, not only the soft, but also very hard things, as you can see here, the omnidirectional mobility and omnidirectional driving, or omnidirectional gripper thing, and so on. And this is the slogan of our groups, Plus Ultra Robotic Mechanism. That's the slogan of our group. And as you can see here, we expand the concept of the robotic mechanism from the dot line plane, as you can see here. Especially this time, let's focus on the line configuration at the middle. Okay, so this is the one of the line configuration, and this mechanism has the really thin membrane from the inner to outside and outside inside. It's a torus configuration, and we build this sort of the robots as a mobile robot. This is the motion of on the rough terrain. This mobile robot can move even this sort of the really moody and very hard environment, as you can see here. And the motion at the top is from inside to outside. But let's think about the reverse motion. So not from the inside to outside, but from outside to inside. This configuration can be used as a robotic gripper, which can grasp very variable objects. So so as you can see here, this configuration, the eversion mechanism can be used not only the mobile robot, but also this sort of gripper. And we developed the passive eversion grippers, as you can see here, to grasp many kinds of objects. To use the jamming transition phenomenon. But the point of our research is not all of them, all of the inside of the body is filled by the powder, but just we use the 3-layered membrane. And just middle of the layer, there is the powder. So it's really easy to deform without any larger pushing force. So that's our original mechanism. And based on this mechanism, it's really lightweight and very easy to deform with very, very large deformation. As you can see here, it's very, very useful for the grippers of the snake-like robots, as you can see here. And it can use the very lightweight. That's why it can use not only the snake-like robot, but also for the drones to grip some objects from the very hazardous area, as you can see here. And not only use this configuration as a gripper, but also it can use as a landing system. So even if there is not a flat environment like a heliport, it can grip the pole and so on the very hazardous area as a search and rescue robots. Okay. So it's very useful, but the one biggest problem is very, very, very easy to broken, as you can see here. Even if the just one push of the very sharpened pointed object, it's really easy to break. So that's why we have to solve this problem. So one of the idea is to put the protection skin. Like this, we use the cross of the which used as the gum bullet protector, and realize this sort of the cut resistance function at the surface of the grippers, and it can grip this sort of the tools, very tiny pointed tools, but it can grip. And the other solution is to realize the soft and rigid changeable strings we develop, as you can see here. So there is a wire inside of this mechanism, and we pull the wire, it can change into the solid mode. But the point of the is the shape of the unit, not the ball shape, but this cup shape. It can keep the shape as a whole, a string shape as a whole. This is sorry, this is soft mode. We can deform, possibly deform. It can be, and yeah, this is soft mode. Okay. And we use these strings, this sort of the fire resistance grippers, as you can see here. It can change its shape, possibly, to negotiate into the grasped object, as you can see here. Okay, and let's make use of this core technology. We would like to expand the concept, not only the single torus eversion robot, but also the branched torus. It's really challenging that we try. But there is some similar concept from the Italian researchers as a plantoloid. So we set the different the animal, the life, as you can see here. It's really grotesque, so please be careful. It's Nemertea proboscis with branched configuration. And this, they are using this configuration to catch some food. Not only that's using, but also this Nemertea used that's eversion configuration as a locomotion. That's really unique. So we would like to realize this the robotic mechanism based on this Nemertea proboscis, as you can see here. Okay, this is our one of our goal, and we observed the real Nemertea proboscis with Professor Kajihara in Hokkaido University, and we checked the proboscis and the tip end point of the proboscis. There is this eversion configuration. We confirmed this. So how to realize this? So we set for this is the first prototype model of the eversion-inspired robotic mechanism with 3-branch version. And we realized this, and as a next step, we how can I say, as practically use this as a deployable of the solar, very thin solar panel system. We use this mechanism, and also we try to. This is not a branched version, but the returning motion is very difficult. But the Tomoya Takahashi, the one of the student, the member in our groups, developed this, and it can it is using the waters inside of the body, not the air. So it's really easy to changing the direction and the returning motion with the really smooth inner guide of the mechanism. And also, he's developing this mechanism. It's really nice application for the welfare robotics for the elderly person. And so as a next, as you can see here, we developed many numbers of the this sort of the eversion robots and the protection, like based on the scale of the life, and also variable stiffness. This is the one of the important concept of our group, variable stiffness. This is developed by the Issei Onda of our in the one of the member of our groups to develop the soft and rigid changing the mechanism with string. And we would like to expand how can I say, now the present model is the fixed position, the branched point is the really fixed position. But let's think about the branching configuration, not on the fixed position. So we would like to realize, this one. To change the position, we would like to realize this sort of the robotic blood vessels, not only to change the position of the branched configuration, but also it can use as a self-feeding function, as you can see. So even if it's cut and injured, it can combine these two liquid, and about 4 hours later, it can recovering, and it can works as a pneumatic actuators. Now we realize a 3 minutes version. It's very quick one, as you can see here. And let's think how to expand the concept from the Nemertea proboscis mechanism. Is this
Kenjiro, is there any way to wrap up your talk at some point?
Thank you. Okay, so now we the focus on the not only the how can I say the material point of view. We are going to develop our research, so edible robots and so on, and the degradable robotics. So this is the most important point in my talk there. So how to expand the concept of the soft. So it means the soft and hard we can change, and that's a really good important concept. But what is beyond soft? So we think the beyond the soft is a degradable one. So it means the distance of each part of the body can be changed. That's the degradable. But how to correct the material of the body, that's the question. So far we take advantage of the differences of specific density. As you can see here, this is a bottling as a material, but one of the way to connect the material is to make use of the different specific differences in specific density. That's our latest consideration. Okay, thank you very much for your attention.
Yeah, thank you, Kenjiro. I see there are lots of possibilities of different embodiment here, and you're literally genius coming up with an unconventional embodiment, and I think this is really in line with what we're discussing here.